Okay, so I'm going to do this problem, and it is from Modern Magnetism, homework number 3. It's problem 1. I'll put it on the video. It says consider an in-plane material, that is one where the anisotropy is easy plane rather than easy axis. This is achieved by setting a negative anisotropy energy along the hard axis. This material is subject to an external magnetic field applied normal to the plane. If that plane normal is z hat, then the energy density of the system is this epsilon equals b mz minus ku mz squared over the magnitude of m squared. And then it defines ku, which is our anisotropy, and it's equivalent to the Dmag field in a thin film. And then it says to use the Landau-Lifshitz equation to find the polar angle of the stable magnetization orientation. In other words, make sure that the time change of the magnetization vector is 0. This basically just means that there's no Larmor torque, so there's no torque at all. All right, so let's just take this one step at a time and look at this conceptually. So we have a thin film, and then this is going to be Z, and then that would make this Y and this X. And what we're looking for is we are looking for the angle. We're finding the polar angle of the stable magnetization orientation. So there's some magnetization vector, and the angle between the normal or the hard axis in this case is the thin film is some angle theta, and this is what we're trying to find. And we're given this epsilon equals b mz minus, it's minus because this is what we were told. We sort of just have to take them at their word that this negative anisotropy is what defines that hard axis. And then mz squared over the magnitude of m squared, and then it defines ku, or anisotropy constant, as this mu naught ms squared over 2. It's a magnitude of ms squared, but it's positive, so it's not really necessary. All right, so this is where we're starting. So it's really the only thing we need to know here is, first we need to know the Landau-Lifshitz equation, which is, I'll just write the entire thing. It's a minus gamma m cross b effective minus lambda, and then this is the damping term, but I'll just write it m cross b effective. So this is the full Landau-Lifshitz equation, whereas this is going to be our damping term, and then this is going to represent our Larmor torque. So it's kind of like our torque. Excuse me. And so, and this is equal to this, okay? I should have put that. This is on the left side of the equation. So, and it specifically says that in the problem, that we need to make sure that the time change of the magnetization vector is 0. So this whole thing is going to equal 0 then. All right. So where we need to start is by finding the field. We need to find B effective. And that's going to be the negative partial derivative with respect to, in this case it's mz, of our epsilon. Now our epsilon, this is an energy density, so this is energy over volume, so it's just something to keep in mind, but we can sort of just ignore that for now. Okay, so let's define a couple of things first. So we have this m vector up here, but with the angle, let's just find all of the components. For example, like mz is going to be our m magnitude. I'm just going to write m after this from now on because we're just going to make it positive, okay? It's going to be m cosine theta is our mz. Now, for me, I always have to, like, to visualize it better, I have to do this top side. So if this is our m, and this is now going to be x, strangely, okay? And then this is our y, just going off of our other picture. And then this is some phi. Oops, I didn't draw a very good phi. Let me do that again. This is phi, better, a little bit better. Okay, so this is y, this is x. This is our phi. So we have our m cosine theta is this line, okay? Or this is actually this line then, I'm sorry, this line here that I drew is m sine theta, right? Because it's, let me switch colors to maybe, let me just switch colors from now on just to, yeah, so up here, right? So this shadow, essentially, that it's casting on this, on our thin film is this line here. And that's m sine theta. And then we need, for x, it's going to be cosine. So if m's sticking out this way, right, then this would be sine. This would be cosine. So cosine phi, this is our mx. Then our my would be the other one. So it would be m sine theta again, sine phi. Okay, great. So we've sort of understood and mapped some things using our physics and our trigonometry. Now what we're going to do is we're going to actually calculate this. Our next step is just to calculate this derivative. And that is going to be yeah, okay. So this, just 1 second here. This minus doesn't belong here. I'm so sorry. This is just positive. It's the change in the energy. It's not the negative change in the energy density. So just doing a simple derivative with respect to mz of epsilon. So that's going to be b minus 2 ku mz over m magnitude squared. Okay? Now, so this problem is stating, it's important to note that this problem is stating that there is this magnetization vector and it is not moving. There's no torque whatsoever in any direction. So that means that m cross b effective is 0. So now we're going to do a quick cross product. Now that we have our b effective, which is this guy, we're just going to do a cross product. So I always do it this way. Say x, y, z. So my bz minus mz by, and then y hat plus y hat mz bx minus mx bz. Then z hat is going to have mx by minus my bx. Okay. All right. So it was stated in the problem that the B field, the B field is in the z hat direction. Okay. The z hat direction is where the B field is, which means anything that's not BZ is 0. So this is 0, this is 0, this is 0, and this is 0. So all we have is we have x hat mybz equals 0, and y hat, this is minus y hat mx bz equals 0. Now, these unit vectors are never 0, so we just occlude those, and then I'm going to change this to a positive because there's a 0 on the other side. I'm just gonna make it easier. That's really it. So now we're just plugging in our bz, which is up here. This is bz, or b effective here. So we get this. We get my times b minus 2ku mz over magnitude m squared equals 0. And then we also have this mx times the same thing. So b minus 2ku mz over magnitude of m squared is 0. Now at this point, the property of this thin film is that there's basically, it's in plane easy axis. So it's an in plane, so it's easy plane instead of an easy axis. So directionally it doesn't matter. It's isotropic in the plane. So that means we can set this angle phi to be whatever we want, and it will not change the result. Okay? So if we set the angle phi to be 0 up here, then that gets rid of my, because sine of 0 is 0. And then that makes our mx just m sine of theta. Okay? So that's just m sine of theta. Because cosine of 0 is 1. Okay? So let's just write that again. mx equals m sine theta. My equals 0. So this is just 0, so we can ignore that. Now we're simplified a little bit. Now we're going to remember our Ku was, what was that? Okay, yeah, it was mu naught ms squared over 2. Now at this point there's two ways to proceed. You can just take the magnitude of m as being m squared equals mx squared plus my squared plus mz squared. You can do this, right? But something that we know from theory is that the magnitude of m in a thin film is always ms. So this is something to know. It's in the book, and it's also just in the theory about thin films. You can do it both ways. You can do this problem both ways, but it's a lot simpler if you just know this. And so we're going to move forward with that. So m, anytime you see m, it is now ms. Okay, the magnitude of m. So we get ms sine theta times b minus, now we're going to plug in our Ku here. So we get 2 times mu naught ms squared mz. What was mz? It was ms cosine theta divided by magnitude of m squared, that's ms squared, and then there's a 2 down here, right? Yeah, okay. So we can simplify this a bit. So the 2's go away, the ms squareds go away, and so we're left with, and this equals 0. Okay. So we get ms sine theta times b minus. Well, you know what? Let's instead of doing this, we're gonna keep this. Instead of doing that substitution, let's put this back to mz just to make it a little bit easier. So this is b minus ms cosine theta. Okay, so now we have something that's a little bit cleaner, and this equals 0. And so we get mz, because at this point we want to kind of solve for make some simplifications. Mz b equals mz ms cosine theta. Okay, and now we're just solving for theta at this point. So the mz's cancel, and so b, oh, there's a mu naught here. I'm sorry, I must have forgot that. Mu naught ms cosine theta. So we get cosine theta equals b over mu naught ms, where theta is the arc cosine of b over mu naught ms. And that is our answer. Now there's a couple of things we can do to like make sure that our answer makes sense. So we can plug in what our mz value was and make sure that we get things that make sense. There's a lot of different things we can do to validate this claim that we've made. But the key thing that I want to take away here is that our b cross m was 0, which mathematically that means that they're parallel. So that means if you have some b field in this, going along a hard axis of the thin film, where there's an m, if your LL equation, if your Lensman-Lifshitz equation is 0, if there's no motion whatsoever, that means m has to be parallel with b, which means that b has to equal mu naught ms, right? So you get this maximum value of b, which is mu naught ms. And I believe if you go higher than that, you get the imaginary values. So you get the maximum value of b of mu naught ms, and if you have that, then you have them being parallel. I think this is the key takeaway we can gather here. And so theta must. Why is that? Because theta has to be 0. And so for the cosine of 0 is 1, that means that the ratio of b and mu naught ms is 1 to 1. So anyway, that's the answer, and we've done it. So thank you very much. I'll try to post more in the future. I know I haven't been posting very much. I've been really busy, but there you go. Hopefully someone took something away. Thanks.